This is my lab report on Lab 3, the black hole simulation. To start out, the purpose of this experiment was to use a computer simulation to find the mass of a black hole by analyzing the orbit of a star that was going around the black hole. And then for part 2, we are supposed to find the velocity of a spaceship that must leave the surface of the moon and fly around the planet in a figure-8 orbit without crashing. The system would be the black hole and the surroundings would be the star in the first part, whereas in the second part, the system would be the rocket and the surroundings would be the moon and the planets. So the physics that works here is the universal law of gravitation as shown, and Newton's second law, which is something we've worked with before, but we can also use Newton's second law to derive the F net of the parallel component force and the perpendicular component force. The assumptions that we're making while doing these calculations are that the black hole is massive enough that any forces acting on it don't do anything to the black hole, and also in part 2 that the planet is massive enough that the forces acting on it are also negligible. Also, we're assuming that delta T is small enough to simulate a non-constant force because the universal gravitational force is non-constant. However, the code can only run in iterations. This is my code for part 1. As you can see in this calculation loop, we start by getting the initial velocities and finding our P initial and P final by using the velocities. And then we find our delta V and our delta P's, which is just calculated as, or delta P delta T, which is calculated as delta P over delta T. And we know that the net force is also the dP dt, so we can just plug that in right there. We also calculate the parallel force along with the perpendicular force as shown, and then we're able to calculate the mass of the black hole reversing the equation from the last slide of universal gravitation and solving for m. As mentioned, we're using the universal gravitation equation just to calculate the mass of the black hole. So we isolate m on one side for the black hole and then plug in all the other values that we have based on our calculations. And we found the mass of the black hole to be approximately 1.67 times 10 to the 34th kilograms. This is the code for part 2. As you can see in this calculation loop, we find the force of the planet on the moon and the force of the ship on the moon, along with the force of the planet on the ship and the force of the moon on the ship, so that way we can get the movement of the planet and the ship. And then they can both interact with each other by using the F nets as shown. Then we also need to update the velocity and the position just so that way we can track the objects as they move in the code. So by using the speed as shown, I was not able to get a figure-8 motion regardless of how I tried, but I was able to get it to change directions very sharply as seen right here. And this is because the force coming from the planet is way stronger than the force coming from the moon. Therefore, any speed that is needed to do an orbit around the planet is too strong to be affected by the moon, and also vice versa. The minimum speed to go around the moon is too weak to go around the planet. So, some possible sources of error is that we can only simulate the non-constant force because the code is iterative. It doesn't constantly change. It, of course, takes steps, and we update it as those steps happen, and we try to make those steps as small as possible so we can do as many as possible. And we're also assuming that the law of universal gravitation is accurate at predicting the masses, because as the force changes, the mass kind of changes very, very slightly in the calculation loop. So we're just using our best approximation. Additionally, in reality, the black hole and planet are not stationary because there are other forces that act on it, and the small forces that also act on it do add up. Therefore, we can't assume them to not move. So the net force and its parallel and perpendicular components are different than the rate of change in momentum, only because the momentum rate of change is easier to calculate as we have what we need by using the velocity. However, it's a lot more difficult to calculate the parallel and perpendicular components as you got to include all the other forces in the surroundings. Now, if we wanted to predict the motion of the entire system, we would have to include all of the surroundings, But there'd also be some dominant forces and dominant interactions that are way stronger than the other ones, and definitely take over and contribute more to the motion than anything else.